All right. Hi, everybody. We are getting ready to get started here. I am just. Okie dokie. All right. So, I figured we would recap some of the things that we talked about last time. I'm just trying to get into the console here, sorry. I am Randall Hunt. I am at JR Hunt on Twitter. I'm here with Sunil. Uh, we are today going to be talking about convolutional neural networks, which is a really complicated thing that I don't know anything about, but I'm hoping I'm going to learn about it today. In the previous two episodes, or three episodes?
Two.
Two. Okay. In the previous two episodes, we have covered the basics of how to set up the deep learning AMI, how to build a multi-layer perceptron model, and then how to do kind of analysis from there. So last time what we did was we used Poly to translate. Well, we used a model to take a pronunciation of a word like aluminum or airplane, or even our names, and we took that pronunciation and mapped it to the way a person with a different accent might pronounce it, and then we passed that into Poly and made Poly speak in one of the British voices with an American accent, for instance. So that was kind of interesting. They used the CMU Dick model and some other stuff, and we kind of got it all working there at the end, at least a little bit. So today, what are we going to be covering? I'm going to flip it over to your screen. Is that all right?
Yeah.
Okay. It's on your screen.
All right. Today we will try and learn more about image recognition and also, how we can leverage convolutional neural networks, which is a type of neural network, to build these things. So the fundamentals that we will learn here are applicable to other image or video related problems as well. So we've gone through basics of neural networks in a couple of episodes already. So we saw the first episode with multi-layer perceptron being used for sentiment analysis. We could solve this problem today with a multi-layer perceptron as well, but convolutional neural networks tend to do really well with images, and we'll see why. So today our task will be to classify or identify given image into a piece of clothing. So our data set actually has about 10 different kinds of clothing and accessories. So we have t-shirts, trousers, dress, coat, bag, ankle boot. All these categories are available, and we have a lot of images there. So it's called the Fashion MNIST data set, and the reason is MNIST is a popular, the handwritten digit recognition data set. And I feel like that has certainly been overused, and which is why I didn't want to take that. Want to take something a little more fun to kind of get started with convolutional neural networks.
So just to recap here, with all of the different machine learning tasks that we're trying to undertake, we go through a series of steps. First is getting data,
Right.
and then second is applying labels to that data, or maybe the data already comes with some labels, which is the easy mode.
Yep.
And then we transform that data into a format that MXNet or some library can understand, and
Correct.
then we build our model. We build the symbolic representation of our model.
Right.
Then we execute that and train the model. Then we save the model, and then we can use it to
Correct.
solve our problems. Okay. So
I'm glad you're been following along, Randall.
yeah, are you surprised I learned something? I am too.
Yeah. Cool. So here's kind of like the data set, it looks like this, and I'm going to share the link on Twitch, um, so that people, oh, I still can't share links, Randall,
Yeah,
on
I got it.
Twitch. Yeah. So, okay, I'm going to make sure I give the link to you.
I just shared it.
Perfect. Um, so this is a fun little data set, and it trains fast. So it's a good starting point. But the concepts here are translatable or reusable pretty much for more advanced use cases as well. Okay. All right. So what I'm going to do is, as you can see, the data set is available. It's actually got some weird, or rather, a compressed format. So I'm not going to write the code to kind of transform this or load the data. What we'll do is go to the MNIST tutorial on MXNet, and we're going to copy the read data, the code to read and unpack the binary and get it into a NumPy array.
I mean,
So
it looks like a pretty reasonable format.
yeah, so I'm gonna share this link with you as well, so that folks can copy the loading part of the code. And
Can we make your screen, your notebook page full screen?
yes,
Or not necessarily full screen, but just like maximized?
yeah, there you go.
Thanks.
All right. Do you need me to zoom it?
I think a little bit of zoom would help, yes.
Okay. I'll keep it here. Cool. So the MNIST dataset was originally hosted by Jan LeCun, and we can just change that path to fashion-MNIST S3 website, EU Central 1, Amazon AWS. So we can change the path. I'm going to attempt again. Nope.
I need to like mod you or something. I don't know why it's not letting me. I'm sending the command to make you a mod, but it's not working. Anyway, I'll keep you can keep posting it in Twitch chat, and I'll
Oh,
post
do you
it.
get to see the link?
Yeah,
Okay,
I can
that's
see
good.
it.
Oh, perfect. All right. Good. And then we can just execute this code, which loads the training label and the validation labels, right? So remember, we're pretty much going to cover only supervised learning tasks. They tend to be relatively easier than unsupervised. And this data set has clean, sanitized labels. And it already comes in a training set and a validation set as well, right? Remember, we split the data into training and validation set. The network only trains on the training set. The validation set is kept aside so that we are keeping in check to see how the model performs. Because we want a generalized model. We don't want a model that is really kind of fixed per se, and over fits into that data set that it trained on. Because ultimately we want to predict with some wild examples as well. Make sense?
Yep. And then, do you have a good estimate for what the size of the training set is versus the size of the verification set?
I mean, relative numbers, people go anywhere between split between 70-30 to something like a 90-10. So I would say like 20-25% is a good number to kind of keep the validation set aside. But as far as actual numbers, it really varies on the problem. So the rule of thumb is more data you have, the better it is for deep learning. But which may not be possible always. So if you have, let's say, a very small data set, like how can we leverage, say, pre-trained models, or what are some of the techniques to do that? And actually, we'll cover during the second half of this, where we'll go with a smaller data set and try and train. So that'll be a fun use case. I've not done this. So I had this crazy idea last night that, the second part, we will build a model to identify if the image is Randall or not. So, so we'll take a stab at that.
Instead of hot dog, not hot dog, it's Randall, not Randall.
Yes. Let's see if we can get to that. I think that'd be a fun exercise. And I'm trying to
point out briefly that the parentheses, being PEP 80 like I am, the parentheses around train label and train image are not required.
I know. It's as I said, I just copied the code from the MNIST tutorial website. So there's a lot of non-PEP8 code I will be writing in this tutorial.
Oh well. I'll try to suppress the urges.
We need to run a lint after this before we submit. Cool. So I load the table. I load the labels and the training set. I've just pasted this markdown so that we can just reference the code here. So the next part is let's just take a look at what data set, import matplotlib. So let's just do the plots inline. So let's display, what I'm trying to do is display like the first 10 images. So matplotlib.pyplot plot.subplot. So the subplot, so I'm creating, one row with, say, 10 images, and this is the index of the image, and plot.im. So I'm going to show the images. I thought it'd be just like cool to visualize, the images that we have. Kind of like, maybe I can script this CMap, but we'll just turn off the axis. We're just displaying images. And plot.show.
So we're just going to show the first 10?
Yeah.
And these are just like 28 pixels by 28 pixels or something?
Correct. Yeah. So it's a small data set. I mean, the images are tiny images.
The coloring, that's because the matplotlib uses like BGR or something. Instead
Right. So what I can do is say do this, and this way it's all grayscale.
Okay.
Cool. So now that we've seen the data, let's actually transform the data, right? So let's just like the classic step, right? We need it to be fed to MXNet. MXNet. Let's just so the thing is, MXNet takes or pretty much every framework kind of takes it in a certain shape, the inputs. So usually it'll be something like, bat size. And for images, we'll have a 3D data, right? So 3D data is the number of channels, the height, and the width.
And the
I
number
think
of
it's
channels
width
in
and
this case is the colors.
yeah, so width and height, sorry. So in our case, whatever our bat size is, um, and it'll be 1 comma 28 comma 28, right? Because our height and width are 28 by 28, and our number of channels is 1 because we're just using grayscale.
Oh, okay. Is that going to make the model have trouble with colors, or is it fine to train it with grayscale?
Well, that's a different question. So it certainly may. I can't really say, but depends actually on uh, the kind of prediction we might be doing. So I'll table that. Why don't you ask me the question in like maybe 20 minutes?
Sounds good.
Because so color, we might learn other features that are color independent, right? Let's say I am detecting a T-shirt versus a shoe. I really don't need the color, correct? But if I'm trying to identify a red parrot versus a green parrot,
Right.
then well, I need the color. So
But even grayscale isn't just one channel, right? I mean, so
uh,
it's not like a
it's
white pixel or a black pixel, right? Because that would be black and white, not grayscale.
but there's intensity, right? So there's a number from zero. Each pixel has a value
Okay,
from zero
yeah,
to 255.
gotcha. So instead of like a tuple of red, green, black, white,
Correct.
gotcha.
Correct. And we're actually going to normalize that. So let's say I'm gonna a little bit bat size. I don't know. I'm just arbitrarily picking a number here.
100.
So just like train iter, right? So remember, we had the ND array iterator, which basically takes, first it takes the input array, the label, right, the bat size, and we have the option to shuffle our input. And shuffling is always good because any kind of natural ordering is kind of disrupted, and the model tends to converge faster when you shuffle the data.
When we were using the one hot algorithm in the
Yeah.
previous episode, was that a form of shuffling?
No, the one hot is a representation of just representing the label or the data in a format that is consumable by the
Fine. Okay.
model.
Gotcha.
So
Okay, I remember now.
yeah, but it does help. What it does is it actually helps the model not assume natural ordering, right? Let's say in this case that we have categories, correct? So let's say t-shirt, ankle boots. There's no real ordering here, right? Um, and we kind of don't want when we are dealing with like sensitive or rather um, like very sparse data sets or just from a correctness perspective, it's dangerous to let the model assume something. So we can one hot encode the labels so that there's some kind of ordering that we bring to the table.
Okay. And Herbert Kelly asked me to turn up my mic, so I'm turning up my mic.
And similarly, we'll do the validation iter. Um, but here's the thing, right? Like we need to convert the data into this 4D shape, right? So we'll just do a 240 um, function, and what we'll do is we'll reshape the image. So the reshape function, takes the so we'll we'll need to get the shape of the image first. So we can just do image.shape of 0, which gives us, so I'll just show an example. It's called train image, right? Let's not just assume that. So we'll just use rather than hard coding, I'm just accessing the channel here. And what we'll do is we'll just cast this as a float value. So what we can do is use np.float 32 divide by 255. We'll just normalize all our pixel values.
Huh. Okay. So this is just taking the array, and we're calling 240 on all of these?
Correct.
Yeah, gotcha.
Yeah. And the label is already in that shape. I think it's called.
Do we need to do some sort of like list comprehension or something, or is it going to work on the whole array?
Because it's actually a NumPy array.
Gotcha. Okay.
So, yeah. So, well, oh, sorry.
Same thing for the validation set.
Yeah. Okay. There you go. That worked. So you can see here, this is the batch size. We've got the data. That's actually a pointer to the data. As you can see, the ND array. And it's assumed that it's, we're still working in the CPU realm of things. So it's actually bound to the CPU. We've got the label. Yeah. So this is essentially our data now.
Okay.
So pretty much, this is pretty easy, right? Like this is an easy data set. Now we can actually start to model already. But, I thought it'd be good to kind of cover some of the basics of what's happening.
I just saw what was on your screen and I am now terrified.
Sorry?
I just saw what's on your screen and I am terrified because this takes me back to high school.
Well, I'm going to scare you for the next 2 minutes and then say, like, you don't need to worry about anything.
Okay.
So the idea here, there are other better resources to kind of go dive into actual math. Again, because we're focusing on developers, we'll just kind of like treat this more, hey, this is all we need to know, and we know this works under the hood, and we're just going to access it like we do like any other APIs. So the intuition here with convolutions, if you remember with traditional machine learning tasks, right? So we do a lot of like feature engineering and identifying which features. Remember with sentiment analysis, we broke things down into words, right? So in this case, we need to do something similar. And what it's proven is over the last few years, convolutions have become this amazing thing to extract features from images. So what essentially we do is we define little filters, and these filters extract features from images. Okay? You're with me?
We define filters. Filters are extracting features from the image.
Correct.
So the filters are numerical in nature, right? It's like less than this, greater than
filter. Correct. A filter is also called a kernel, and and they happen to be matrices like these because we are dealing in 2 dimensions, right? Images are 2-dimensional, and we basically define these filters, and we run those filters through the matrix. So as you can see here, let's say our filter is, this becomes our filter. We run the filter through the matrix. So what it's doing is it's doing matrix multiplication, and we get the outputs transformed, we capture the outputs as we convolve through the matrix. And I'll build up intuition on what the filters do. So here's actually an example of for different filters what happens. So as you can see, a certain filter like this filter happens to identify edges in a certain direction. This filter, again, a different direction, and this filter seems to identify more like edge. So it's kind of like edges in kind of with an angle, and certain filters can blur, they can sharpen, they can identify textures, and so on.
So Herbert Kelly is looking at these and asking, are they always a 3D matrix, i.e. RGB, specifically referring to images? Or can it be anything?
So convolution in general is you can do in any dimension. So you can do a 1D convolution, you can do a 2D convolution, 3D convolution, and so on. Depends on like how your input is structured. In this case, we happen to have our images into as a 2D matrix, and which is why we will just do a 2D convolution.
So we're using the word convolution a lot, but I don't actually, I know that it is an operation that you perform on a matrix, but I don't remember how it works. I don't remember how to convolve something. Is that something that you have time to cover, or?
I don't, but I have links. I'll share links to do like the mathematical intuition between convolutions. But for the sake of this lecture, we can just say, we use filters, and we'll run the filters through images to extract features, and we'll work on those features to do our image classification.
And is there anything stopping us from running all of these filters in parallel?
Not really, because we're not, we're doing it independently.
And that's probably where we can get a lot of gains in terms of speed, as we can say.
Yep.
We have feature maps for like 28 features that we've identified. We're going to run all 28 at once because we have it on the CPU or GPU.
Yep, absolutely. So what I'll do is I'll just play this little video, and
Can you make it all the way big, or?
Yeah. This should help kind of get an idea. As you can see, we ran a certain filter with the edge, slightly slanted in this way, and it identified. This essentially is the result of the convolution that we did, and it is identified. This is the feature map.
Okay.
Now, similarly, there's a different. You can see. The green one. One was with an edge in this direction. Other one was with an edge in this direction. So you can kind of imagine that we can build a bunch of these filters to extract many features.
This is how OpenCV works, right? Because it uses something called HAR cascades, and it just has a map of all those features, and those are designed for finding faces. I remember this.
Yeah. Yep. A lot of, for example, a lot of early blur detection algorithms use filters or Laplacian, edge detectors or canny edge detectors to kind of find the edges, and depending upon how many edges that you kind of find, you can identify if image is sharp or not, because if you have more edges, the image is sharp. If it's blurred, then it's kind of smudged, so you don't find many edges, right? So a lot of that is actually built in to this. And we don't need to explicitly kind of go extract these features. As you'll see, the framework does the heavy lifting for us.
That's really cool. I've always wondered how this works, and like everything just sort of clicked in my mind right now. So
Nice.
it's just math, right? It's just taking a matrix. When people say the
It,
word kernel, all they're talking about is just a matrix, right? That you
exactly.
apply across the end. Okay.
Correct. As you can see here, right? So we can just do this. We can just multiply with this filter, and we now have a blur. We can define our own blur filters.
I feel like I should have known this 10 years ago.
It's okay, not too late. So the next thing is we will run we'll pass through an activation function because we need to remember, if you remember, we needed to add a non-linearity to be able to kind of classify, or rather map to a much higher dimension, right? So we're with some of the traditional machine learning algorithms, which are linear classifiers, we can only do so many things. With nonlinearity, we get more degrees of freedom, and we can solve more complex problems. So we'll run it through an activation function, and this is just an example of the activation function to once it's passed to the activation function after the feature map extraction, how it looks. The next step is actually something called as pooling. So, if you kind of do like 28 into 28, which is 756, that's a lot of like, it's quite large. Now imagine if we were working with, 256 by 256 images, then it just becomes way too large. Now, the intuition is, I don't really need an image to be that big to say it's a cat or a dog or a T-shirt. I just don't need it to be that big. So what we do is an operation called pooling, where we reduce the size of the image by taking the max of adjacent pixels. Now, again, since this is 2D, we'll basically say, hey, max pool of 2 by 2 filters, and we'll pass it just like the convolution. But the operation here is, if we say it's max pooling, we'll take the max of the adjacent pixel values. We can do average, and so on. Does that make sense?
I get it. The reason we have to do this though is not necessarily mathematical. It's more computational. Like it's
exactly.
Okay.
Yeah, because hey, we can do faster matrix multiplications with this. We don't really need to have a much bigger image or matrix to work on.
So it's basically like when we have something that is small enough to fit in a register or fit in a cache, it's going to be way faster than if we have to pull in a megabyte worth of feature
Correct.
every time.
Yeah. Yep. So okay. So now that we know about convolutions, let's actually start to model. So we'll use one of the most basic convolutional network that Jan LeCun proposed way back in '95 to do hand-digit classification, and we'll see how we can change maybe different functions and activation functions and see if we can improve the results from that basic network. So as usual, we declare our placeholder variable data, and then we'll start declaring our convolution. So we'll do mx.sim.convolution. So
we've never covered convolution before. So this is a new part of the MXNet API.
Correct. So let's look up.
And is this just the convolution operation?
Correct.
Okay.
So the convolution API It's pretty cool. We just need to send it the data, and so it's, as you can see, there are different kinds of convolution here, right? So we can give it the data, the kernel. The kernel is essentially the size, right? So is it 3 by 3, 5 by 5? What's our kernel size? Stride is, do we skip certain steps? It's the window size, right? So if do we skip two things? Stride of 1 is essentially we'll just go one by one and slide the window. If stride is equal to 2, that means that we will skip a couple of columns and then slide the window. So things like that. So it's all built in, and we can just specify the number of filters, and the framework will figure out what filters it needs to generate and actually do that for us.
Wow.
So our API looks, trying to find actually the wrong word. Sure. I was trying to find a example sample here, but all right, there you go, convolution. So we'll say data equal to data, and then kernel, right? So kernel, we'll specify our kernel. We'll just say 5 by 5 kernel. Again, we can use 3 by 3. I think this would be a good start. So number of filters, we'll go with 20 filters. So the next step is to send this through an activation function, right? So mx.send. We can just say activation. So there are the very and you can see data equal to con1 here. There are different activation functions. So we'll have like tanh, sigmoid, relu. The most common one is relu, but that was proposed back in 2012. And since we are using the most basic network, which is 95, I thought it'd be just good to kind of cover and play with different activation functions. So we'll still go with the primitive activation function to start with. There you go. These are the activation functions that are available for us. So sigmoid, tanh, soft relu, and relu. So sigmoid, the reason why these functions are helpful, they add nonlinearity, right? So functions. Let me see if we have. Right, here you go. If you see the shape, right? So they have a nice S shape with like sigmoid and tanh, right? What that means is they give these, they kind of like clip either the inputs between like 0 and 1 or -1 to 1. They kind of give this nice shape where, because this is a continuous function, we can differentiate through that, and we can, this adds the nonlinearity, which is important to give us more, so to speak, degrees of freedom to help with, finding that crazy function shapes, which will allow us to do more complex tasks.
Because we're basically trying to find a function that will map to whatever our input is.
Yeah. So if you remember the neural network equation, right? So it's basically wx plus b, where x is the input and w is the weight matrix. We're trying to find the weights for each of those connections in our network. So like that's our task. If we had linear weights, then it's just a linear combination. We won't be able to find the best weights, or rather, it becomes a simple function. We need a very complex function, and adding the nonlinearity helps us get there.
Okay.
And I mean, that's the intuition. I'm trying to not scare the audience.
I'm scared.
Okay. So the next idea is adding the pooling layer. So mx.sim.pooling data equal to activation 1. And let's look at the pooling layer. There you go. Similar pooling. It takes the data out. It again takes the kernel. We can have a pool type and a stride. We'll just let all those to defaults, and we'll just say pool type equal to, we'll just use max pooling.
And that's just going to do
So
the algorithm that you described earlier, where it collapses based
yeah,
on the previous pixel value.
yeah, and you can try average pooling and other pooling. Generally, with images, people tend to use max pooling. Average pooling kind of like deforms the images. Like that's kind of my intuition behind. Um, but people tend to use max pooling a lot in terms of like image recognition stuff. Again, there might be a better reason for using max pooling, but I feel, as I said, like uh, it still kind of retains the image when you pull down, rather than an average, which kind of like smudges the entire image, because the adjacent pixels kind of get uh, um, smoothened out, right?
Okay.
Does that make sense? Or
Gotcha.
so we'll do yeah. So we can just leave it here. So
I kind of, so I get the intuition behind how portions of adding the nonlinearity, I get the pooling, I get the activation function, and I get the convolution, but I don't fully grok how you're doing a 4 pixel kernel for the max pooling, and then you're doing a 25 pixel kernel for the convolution and the features,
yeah,
and I feel like that stuff is still kind of like arbitrarily chosen, and you like max pooling. I guess the 4 pixels, that
yeah,
makes sense. That's pretty straightforward. But the kernel size and
yeah.
stuff like that, I don't.
So the kernel size again, like depends on people tend to use 3 by 3 or 5 by 5 are generally the two kernel sizes that we tend to use. Um, why I chose 5 by 5, because that was originally again, I'm trying to recreate Jan LeCun's Linnet, the first kind of like convolutional network, right? So hence 5 by 5, and that's what he empirically found to be better. But people kind of starting with convolutional network, I would just start with like a 3 by 3 and 5 by 5, see kind of what results you get, kind of look at how the convolution operations happen, and we can visualize this as well. Kind of gets you an idea of hey, my convolutions are too big, um, and I'm not getting, like my network's not training, so I can add more filters, I can reduce the number of filters, and so on. So there's a lot of experimentation that we'll need to do to arrive. What I typically do is look at kind of papers or other networks that people have built, and try to replicate their hard work, and kind of go from there as a good starting point.
Okay, I
So
get where you're pulling it from. I don't have the intuition yet to I think I would just be copying and pasting from papers and
Yeah,
working from there.
that's a good step. That's a good
So,
step.
and this we're defining this convolution, this activation, and this pooling as a single layer, or is that actually a couple layers?
Um, so they can be grouped together because we the convolution and the activation kind of fuse into a single layer. So the convolution output goes to the activation, and then we say, hey, there's a pooling layer that maps this down. And what I'll do is I'll visualize the network after we create it, so that we can walk through how the array sizes or our ND array sizes kind of change through the entire network.
Gotcha.
So um, so we'll just do a two-layer convolutional network. Remember, like with the multi-layer perceptron, we had two fully connected layers, which made the multi-layer perceptron. So we'll do a simple model again. So I just copied the same things above. So some of the state-of-the-art networks, Randall, have like 1,000 layers, somewhere between 100 and 1,000 layers as well.
But those are
So
programmatically defined, right? Like people are
correct.
going in.
So
Okay.
so as you can see, right, like there's no reason why we can just define like a convolution factory helper
Right.
function to generate both of this, right? So I'm just gonna lay it down because it's a simple network. So I'm not gonna add another function here, but you can see that we can add a helper function and essentially generate a bunch of these convolutional layers all at once.
Wow. It's a whole other level of abstraction.
Yeah. So what we'll do is we'll just add 50 filters. I'll pass the convolution 2, activation function 2, and pool 2.
And does
Now,
the convolution, the data coming in is supposed to be the pool one, right? Because we're just passing things down.
correct. Yeah. So
Okay.
this is how this is how the chain continues.
Gotcha.
So what happens is, let me try and find a good example. That I had. Let me find a good image. Okay, this is a good enough image.
So we have a question
Okay.
from Herbert Kelly. He says, "So will a 2x2 be 4 times less processor intensive than a 4x4 kernel?" And my intuition there is actually that with 2x2 and 4x4, that's a difference between 4 pixels and 16 pixels. And to the processor, that probably makes very little difference because the registers that it's using and everything are built to hold, you know, a byte at a time, or however many bytes at a time that they're supposed to hold. So with smaller kernels, I would imagine the processing difference is fairly small. But once you get into larger and larger ones, then you do start to see that linear increase in processing time. Is that a correct intuition,
I
or am
think
I
that's a
way off
fair,
base?
yeah, I think that's a fair intuition, Randall. I don't know what the exact size is. Again, with the GPU, right? Things are done parallelly. These days, the GPUs tend to have larger, cores. So I don't know where the breakpoint is in terms of, kernel sizes.
But theoretically, like, once you get to a certain point, the amount of processing work required does increase linearly with the size
Yeah,
of the. Okay.
yeah, I'd say so because again, it's matrix multiplication.
Gotcha.
Okay, so here's an example of how things look end to end in a network, right? So let's say we have a car. Our, as we saw, certain filters. So these are kind of, let's just say these are filter visualizations in layer one. And initially what you'll have is the filters will learn edge orientations, as we saw in those videos, right? So this filter tends to like, the edge in this direction, this filter in this other direction, and so on. And certain filters will get affinity to texture or other things. As you can see, this is not an edge filter, correct?
This is like a blur filter, I guess, maybe.
Yeah. I mean, I can't really make out what that probably is. Maybe I don't know, some kind of texture, color. But what happens is, as we go further, the next layer builds on what the previous layer has learned or has detected. So the learning is hierarchical, right? Things are built on top of what things have been seen or learned in the previous layers. You see where that's going?
I do. Out of curiosity, though, the third picture here. So it's got the Audi, it's got the edges, and whatever other kind of feature sets it's supposed to be checking for. This third layer, are those features that it has derived?
Correct. It's built on the previous layer now. What
Wow.
it has done is constructed, as you can see, it seems like there are different cars, and it's kind of identified what an average car looks like. And you can see it's from different angles and orientations that it's actually detected the cars.
Okay.
Right? So that's kind of what we're trying to replicate here. And what happens usually is, you can see here there are a bunch of convolutions, and the size reduces as we go further, and that's probably representing pooling. But towards the end, what we need to do is we're in a very high dimensional space. So what we do is we add a fully connected layer to kind of basically gather all this information from all these neurons in the previous layer and kind of map them to a lower dimension, right? So we are mapping things and squishing them, together.
And do we do multiple fully connected layers, or is there one?
Yeah, people do that. So
Okay.
it depends typically on how large the feature set we're operating or dimension we're operating in. So let's say, we had a layer with 10,000, feature map, right? Like we've learned like 10,000 feature map. And if we kind of map that down to, let's say, 10 nodes, fully connected, a fully connected layer with 10 nodes, well, we're going from a much larger, like, space to a smaller space. So we might lose, we risk. Yeah, so usually what people do is kind of break it down, say, go from 10,000 to say 500 to then, say 10. So that's usually done where you'll have multiple fully connected layers. Uh, Rather than going from really large space to a smaller space, you kind of like slow it down.
Gotcha.
So we'll do the same. So we can do is we'll add our flattening layer. We'll just call it flatten, right? So because we're just squishing everything into a 1D array. It's easier to operate. Pull 2, and then we'll call our layer FC1. We can just call fully connected. There are other networks that kind of, if people have worked with other networks, it's called a dense layer. Dense because it's fully connected. So those terms are interchangeable.
Okay.
Yeah. So so if you kind of like see here, right? So you go from this fully connected layer. You can see it goes from 5 nodes to 3, because I think they're only classifying 3 outputs. In our case, we'll reduce it to like 500 to start with.
Okay.
And then remember we need our nonlinearities, and then we'll send it through our second fully connected layer here. And this time we'll use 10. Can you guess why?
Because that's the number of categories we have.
Correct. This is going to be our last fully connected layer before the network. So Lynette, softmax. So we'll add our layer called as a softmax output layer, which is a really common when we use category, essentially categoric classification tasks. So what softmax does is at the last layer, it converts, say, our predictions into probabilities. So it's really nice to kind of rather than having binary values, having values where hey, we predicted it was likely to be 5% likely that it's category 0, 10% that was 50, and so on. It helps the network learn better. So it's easier to, rather than having, if we had like step functions, right, like something that is binary, we wouldn't be able to differentiate through that. So because we have because we're adding these in case of softmax it's negative likelihood, it's easier for us to compute, or we can actually compute gradients, and the network can learn better.
So does it need to know about the previous layers in order to compute that, or is it enough to just have that last fully connected layer coming in?
So what happens is,
because I know there's a W, right? And
right,
then it does the back propagation.
Correct. So what it does is we basically end up calculating so essentially we'll have outputs here, and the outputs will be in the softmax layer actually probabilities. So let's say it's going to be something like 0.1, 0.8, and 0.1 again, right? So that becomes our output. Now what we'll do is based on our loss function. So in this case, the most common one is called a cross entropy function, and what we'll do is that loss function tells us how off we are from the actual predicted or the labels to be predicted. So in this case, let's say we were predicting it to be an oddie, which is, let's say, category 2 or category 1 here. Let's say 0, 1, 2. What we'll do is we'll calculate the loss function. Will actually tell us how how different we are or how off we are from the actual predicted output, and then we'll calculate the gradient. Now this process is called the gradient, right? So we are calculating the gradients with respect to the loss function. We'll calculate it here, and then we will we'll actually do the correction, and then we'll do it to the next layer. So the previous layer, and so on. That whole process is back propagation.
But we're only following a single path back for each predicted output.
So it's done per layer. Yeah, it's done per layer.
So the fully connected layers probably take much longer in back propagation than the layers that aren't fully connected.
Well, it just depends on the number of parameters at that layer.
Gotcha.
And
So
in
it's
this
dependent
case,
on the
actually,
number of nodes instead of the number of
correct. Yeah. So in this case, the conv layer 2 is the one that's going to take the most time.
Okay.
Actually, there is a way to visualize how long things take as well. I had written it's actually a blog that I had written where which shows you there's an MXNet profiler where you can actually view the uh, yeah, let's see. There you go. I'll show you guys that. So there's profiler support.
Wow.
So we can just set the profiler, run the code, and you can just do let's say in your favorite browser, you can kind of see the slices between how long your network operation, your DNS, waiting, all that, wonders. Similarly, you can generate a JSON file and load it in this case, I've used Chrome to see where, it spends most of its time.
That's pretty cool. I know we're a little pressed for time, so I can stop asking questions if we need to keep moving.
Okay.
Sorry. It's very
No
interesting
worries.
stuff.
No. Yeah, as long as it's helpful to the audience, I'm happy to answer. Okay. So I'm going to use the visualizer. So mx.wizplot, wiz.plot network. So we'll just give it the shape. So shape, it's just a dummy variable for us to, or a placeholder variable for it to actually see or compute how it's going to look like when we send the data in through the network. So we did a 1 into 28 into 28, right? That was our matrix. We ran it through a 5x5 kernel and 20 filters. What happens is because see, we get the matrices that say 28 by 28 into 5x5 kernels gets us 24 into 24, right? You see the size actually reduces because it doesn't quite fit exactly, right? Like because we use an odd number kernel, so we actually reduced the original image size into a smaller one. Do you see this? It's actually 20 by 24 into 24. Do you know why?
Why it's 20?
Yeah, because we use 20
That's
filters.
the number of filters? Yeah.
So we get 20 different 24 by 24 matrices, each for each filter. Remember, you're asking, can we do this parallelly? Right?
Yep, totally.
We can. So we send it to the activation function, which is applied to the entire matrix. We send it to the pooling layer, and the pooling layer reduces, as you can see, to a 23 by 23 matrix. We send it to a 5 by 5, 50 convolution. It further reduces, but now we have 50 different matrices, right? Make sense?
Yep. I'm following.
And then we flatten the array, the matrix. We get this. We send it to the next fully connected layer. So we basically get 500 features. We further reduce that, and our last fully connected layer is 10 because we have 10 categories. Okay.
Gotcha.
Okay, so
Do we
let's
have to
now
tell it what the categories are, or do we just do that later outside of the model?
Here. I mean, the model is just going to output numbers, right? 0, 1, and so on.
Gotcha.
It's just the index of this. So we'll use this lookup table once we so import logging out get logger. I think set level, right?
I think it's all caps.
I think it's capital, right?
Yeah.
All caps. It's probably okay. Context equal to right.
And that says just use one GPU.
Yep. Let's say number of epoch equal to. We'll just do one epoch, just to kind of test. It's always a good practice to kind of send the network through one epoch, see what's happening, just kind of like get a feel for the network before you actually run it with everything.
Okay.
So this is a best practice. Module. I think it's, yeah, one dot module. And what we're going to do is specify the symbol. In this case, it's Lynette, and we're gonna say context equal to CTX. Now we need to bind. So bind the network, and we need to give it the basically it takes the data shapes and the label shapes. So what I'm going to do is basically the train iterator has these shapes already. So it already has it inbuilt because we built the train iterator. So rather than hard coding it, I'll just extract it from there. So we can just say provide label of 0. Provide data of 0. So I can just do the shape. Actually, it takes because we can have multiple inputs and multiple outputs. The data shapes and label shapes actually take a list rather than a single object.
Okay.
Does that make sense?
Yep.
Okay. The next is actually calling the fit function. So call the fit function. It takes the train iterator. That takes the validation iterator. And my room lights just and now it's back up.
That's how you know you've been coding too long.
Or be stationary. So optimizer, right? So remember, we'll use the basic optimizer, stochastic gradient descent. We've used Adam before. We can try. We can try Adam, which is the more advanced one. We'll try that later. We'll just use one hyperparameter here. This is the number of steps in the direction we go. We'll choose a faster learning rate.
So we have optimizer twice there. Is that supposed to be a different variable?
Yeah, optimizer params, I believe. Yeah. We'll see. What else am I missing? Fit, and I think that's it. Oh, actually, let me specify. So evaluation metric equal to accuracy. Accuracy because we're just doing categorical. So if it's just going to be a direct comparison. So our final label output will be like, hey, it's 5, and we'll have something like saying, hey, the true prediction was 4. So in that case, the accuracy metric will say 0. Right? It's just a binary metric. It just tells us how many things we got correct. Batch and so I'm just using I'll use this callback function so that I think we've used this before, just to kind of see how we're doing. So speedometer.
Well, we've never used. We wrote our own callback last time, but this is cool.
Yeah, so we can just say speedometer and say the batch size every 200 batches. Do this, and we shouldn't forget the number of epochs equal to num epoch. Okay, let's see. Okay, fit function, maybe, I think it's epoch.
Yeah, I think it's...
Okay. There you go. Oh, look at that.
Whoa, that jumped up.
Between batches, right? Look at that jump. That means that things are going well.
So that was in one epoch we got to 70% accuracy, or almost 80%.
Yeah. Yeah, 77% accuracy. That's not bad at all.
So if we bump it up to 10, is that going to be too many, or?
No, that's no. We'll see what happens there, right? 10. So while the network is training, what I'm going to do is I'm going to get the prediction function ready, right?
Okay.
So let's say actually we can get the predictions of the entire validation set by just doing something like net.predict iter. We can just give, and it's going to predict for the entire validation set. Actually, I'll show you something. Look at how slow that is, right? Let's actually. I'm going to try and use all my GPUs. This is how easy it is to do multi-GPU training.
You have 8 GPUs.
Yeah.
What is this, like a G3 8x large?
No, it's a P2 8XL.
P2 8XL. Jeez.
Hopefully, I have nothing else running. Running fast. Okay, so what I'm gonna do is actually let's pick a index. Say 30.
It's actually going slower than it was on one GPU, but I think it'll go faster when it gets to the bigger layers.
Actually, we need to time that. Yeah, we need. That's a good point. I actually forget how big the data set is. So using multiple GPUs necessarily doesn't mean things are going to train fast. So the reason being, remember, like all the gradients. So what happens is every GPU gets. You know what? My batch size was not up. I just used the same batch size. So it actually. You need to use a larger batch because all the batches are being distributed across the GPUs, correct?
Right.
And the gradients need to be synced or calculated on per layer. So what we are seeing is probably network synchronization issues.
Well, it's more like it's also paying the cost of shipping all that data from wherever it's pulling it from, RAM in this case, over to the GPU.
Yeah.
And that interconnect is slower.
Correct. So when you have larger data sets, you're likely to get things faster with multiple GPUs. But if you have a smaller data set, probably sticking to a single GPU is probably better.
I mean, we were doing 7,000 samples a second on a single GPU, so we're still...
Right. So let me just, I think this is a good exercise. So
Changing your batch size?
Yeah, let's do that.
Do we need to re-execute the other layers too, or yes? Okay,
no, it's the same network, right? It's the same network. This was faster. Remember the last time it took 16 seconds?
Yep.
It now took only 10 seconds. So there you go, right? So remember, like this is a good lesson, right? Like you can't just arbitrarily go multi-GPU. Your batch size needs to kind of reflect because you want enough computation. You don't want to break it into really small tasks where network becomes the bottleneck.
Right.
See, that's better. Okay. Plot.im show. So what I can do is
I'm gonna run go get a soda really fast while you're typing
okay,
out this prediction.
right. So what we'll do is grays are. So just display the gray. So we'll just display the image that we want to predict on. Similarly, plot.show. Actually, plot.axis. Turn off the axis. Okay, all the predictions. Now, what we can do is the probability is spreads of idx dot as numpy. Okay, and 87% accuracy, which is not bad. We should probably train it for more epochs and see what happens. So
If
predicted.
If you get to like
Sorry.
87% and then it's only going up maybe 1% per epoch after that, is there anything that you can do? What does your intuition tell you about trying to make it increase more, or is it just pure number of epochs?
Yeah, that's a good question. So you kind of get diminishing returns, or rather, I think I have a graph. I think I did it here. So let's see. So your loss function kind of goes here on a per epoch basis, right? So look at that graph. Initially, you get like large returns, or the loss function really goes down, and then it kind of like slows down. So which is pretty common, and this is a good shape for how your network kind of should look like. So more epochs, you kind of get to an accuracy that you can determine, and people do a lot of tricks to get that last couple of percent. People do a lot of crazy things. What some of the most common ones are, you kind of like lower your learning rate, you start playing with different batch sizes, and you do those kind of tricks to get to that last level of greater accuracy.
Okay.
So we can do prob.argmax, and then okay, let's see what happens. So that is
A purse. I predicted it.
Yeah, let's see. What did I do wrong? Prob.argmax.
I think it's supposed to be argmax, right, instead of agr.
Oh yeah, sorry. Yeah, let's call it argmax. So predicted is 8. Huh. Remember what 8 was?
I do not.
Actually, 1 second. Prob.
So we can get the probability from the softmax.
Yeah, so predicted. I'll just T F. All right, that's about 99% that it's category 8. Woohoo!
Is a bag.
It's a bag.
All right, cool.
Let's let's not rely on a single data point.
I was hoping we would rely on that. It's a shirt, 94% probability.
That's a pullover, right? Like it's got the sleeves.
Gotcha.
Yeah, the images are too small, so it's a little hard for us to. Let's take something that is obvious. Now that's That's an ankle shoe, right?
Ankle boot.
Ankle. There you go. I believe that. That's a shirt. No? Or a sweater. That's a shirt.
It's a sneaker. It thinks it's a sneaker. Oh no,
No,
it's
it's
a
a shirt.
6. Okay, sorry. I was looking at 7. Yep.
Yeah. Now we index from 0.
Yeah.
Okay, so there you go. That was our first convolutional neural network.
Is there so I know that you talked about optimizers. Is there a way of, for instance, this has a probability of 55%. Is there an optimizer or a method that we can use to go and find the ones that have lower probability and increase their probability? Is that
Yeah, so that's good, right? Like, so our network really, we saw just 87% with 10 epochs, right? So I'm going to use a different activation function, okay?
okay?
And I might just increase the number of filters a little bit. I don't know.
So the activation function we're using now is ReLU?
Yeah, ReLU, yeah, which is the more modern one. And pretty much every network just start with ReLU.
Okay.
Okay? Okay, let's see what happens. I don't know. This is just intuition. I have my fingers crossed to see what the network does. So
It's pretty good.
okay.
To 67% after 1 epoch.
It's a little slower, right? We added more layers. As you can see, we added more nodes, right?
Mm-hmm.
It was taking us like 10 seconds. Now it's like 13.
I'm eagerly awaiting each one of these. Well, I mean, we're already pretty much, we're 7% off from where we were last time.
Yeah.
And that's only after 2 epochs, so.
There you go, 84. So hopefully we'll do better. So yeah, the intuition is again, again, we used a SGD, which is again a little slower in terms of the optimizer. So we could have tried Atom, we could have tried different. So the whole concept of like hyperparameter optimization itself is a big area, and you can play with the batch size, you can play with the learning rate, you can play with the optimizer, all of these things, and try and find a really a better network or better parameters for a given network. That's, I think we're getting close to where we were.
I mean, we're about to hit 90%.
Yeah.
So, I mean, 88% was what we got to last time, right? So it's already
Correct, yeah. So we've saved like 3 epochs. I mean, validation accuracy is the one to look for, right? Because we don't want the model overfitting. So the moment like validation accuracy starts dropping, we know that the network has really learned very well. Well, we've made an improvement of 1%. There you go.
worth it.
And this is again like we can add a third layer. The deeper we go, the better we probably could do. So I'm gonna try and do that last experimentation, and I'm gonna kick that off. So I'm gonna do something like 50 and okay. Okay. While our network is running, yeah. So while the network is running, let's go attempt it. The fine tuning. Okay, I'll show you guys the filter viewing a little later. But yeah, so what do we do? What do we do when we don't have enough data, right? So that's a good question. So there's this concept called as transfer learning or fine tuning, What that means is we can use networks that have been trained on another data set and leverage the same model to do other things.
So
Now,
we can take some of the layers and then apply our layers from those.
correct. Because remember, hierarchical learning, right? I told you that we learn features like edges and edge orientations initially, and then things get built up on top of that. And it's the final layer where the outputs get mapped to the labels, and that's how the network learns. So, so what we'll do is, where did it go? Yeah. So what we're doing is we'll take a model. So ImageNet is a competition where the data set has about 1.2 million images. It's the most popular benchmarking data set out there for deep learning networks. And it's pretty comprehensive. And it's got labeled 1,000 categories. It's identified a lot of, it's got like cats, dogs, cars, plenty of different labels. What the intuition here is the network has learned all these nice features, and we can apply to other image models as well. So because the way we'll identify a face is kind of similar, right? We'll get edges and edge orientations. The intuition is, can we try and use what the network has learned to detect images that are random or not, right? So that's the intuition here. So the steps to do that, the two kinds of transfer learning. What we can do is we can freeze just the last layer and run the model through, just train that part by fixing the weights, or we can reinitialize the entire network with different weights as well. So we'll do the former, and what we'll do is we'll freeze the other layers, and we're only going to modify and train the last layer for our data set.
Okay.
Okay, this is going to be a little faster. So what I'm going to do is I'm going to refer to some of the code in the MXNet notebook GitHub, and we'll use the code from there and transform that code for your data set.
All right.
Okay, so rename, what should we call it? Randall or not? So the MXNet notebook tutorial has some really cool, for example, it's got the fine-tuning cats versus dogs. There's an example here. The only thing is we'll need to convert the images, so that might take some time. So let's download a network. So let's download a. So MXNet has a model zoo.
Mm-hmm.
Which basically has all these pre-trained models. So some of these models have taken like a month to train, cost like upwards of $10,000 to $20,000 because it's been a lot of time that's spent. So we can just go download these models and train on top of them. So it's very efficient. As a developer, this is probably what you'll end up doing a lot, is taking pre-trained models and then fine-tuning them for your use case. Because not everybody can afford to spend $20,000, $30,000 and train from scratch. Also, you might not have the data set which is that large to be trained from scratch. So upper function. So here we go. So we get the fine tuning. So as you can see, here's what the fine tuning model does. So we pass the model file, if you do sim.get internals, it gets all the internal layers, and as an X, so print all layers. Get function. I just want to display the model.
So we're gonna visualize it again, or
Yeah.
we can copy that from what we did earlier.
No, there you go. Yeah.
Okie dokie.
So num classes is going to be 2 because
Randall or not Randall?
yeah. Well, not symbol. I forget. Get. Oh, sorry. I'll display it a little later. I forget the actual command. But essentially, it's you can refer to the layers here, and we'll just get the last output layer, and the layer name happens to be flatten 0. And I think I feel like I've had it somewhere in the code here. Okay. Anyways, we'll just reset. So we got the last layer, and what we'll do is we'll just initialize the fully connected layer, and we'll get the softmax output. So we're just replacing the last layer. So remember this image? We're doing this part. We're replacing the last layer, and we're going to train on that. Does that make sense?
Yep.
Okay. All right, but before we do that, we actually need to we'll need to kind of shape the images. So we'll use iterator. So data iterators that we're going to use. So I'm just going to reuse that, which is going to be in a binary format. So for example, we need to create these record IO files so that things are Randall or not. So I'm going to walk through how we are going to create that data set. mkdir data. And Randall, you said you had your files.
If you just do AWS S3 sync dot or to do S3 ranman dash selfies RANMAN.
Yeah. Sorry.
That should do it.
Okay. Whoa.
There's 6,000. Do you want me to do fewer than that?
No, that's fine. That's fine.
We might want to filter out and get rid of the ones that are like less than 60 KB. Also, I don't know how appropriate all of these are.
We'll see. Anyways, we've not done this, so we'll see how to do this.
Yeah, there's this bug in the AWS S3 sync thing because the list object command returns 1,000 by default, so it always only shows approximately 1,000 files remaining. Until
I just look at the bytes, the total bytes, and that gives me an idea. Okay. Whoa. I think I should just stop it now. What do you think? I think that's enough data.
Sure.
Well,
If
only
you do
got.
ls,
I'm gonna try and get at least 3,000 images. So what we need to do is, I'll just explain the next steps so that I can run through them. We'll create a basically training and validation set directories, and we'll like label them, say 1 and 0, just so that it's easier for us to, work with this. And then I'm just going to move some of these files around, and we're going to execute these commands to create record iterator files so that it's more efficient when we train.
okay.
So I should have probably done the data processing, but this is a live show. Mkdir train / I'll call 0 random. Okay. So move. Okay. So I've moved everything there. So what I did was I went to FW dataset. So there's a face database, and there's a bunch of like celebrity images that are present here, which I downloaded, and that's going to be our not random dataset.
Okay. Are those celebrities, are they labeled?
Yeah, they are labeled.
Ooh, I might use that for another project.
So, right, so there you go.
Oh, nice.
So I'm gonna.
Is Elon
I think
Musk in there?
I don't know. So I need to copy all these images over. Okay, let's see. Let's do some bash here. I think I have a list of. Oh man. I thought I had a file. No? Wow.
Can you like ls-la grep?
Anyways.
Are you trying to find a command that you ran previously, or?
Yeah.
If you do Control R and you type the beginning part of the command.
No. Sorry, I'm actually trying to find the. So I generated the file. Yeah, there you go. Celebimages.txt. That's what I want. So I have these images. So for, let's say, for F in cat celebimages.txt to mv. So I'm going to move the file. What's the train data train 1 not random. Done. Okay.
That is some bad.
You see what I'm?
I see
Sorry?
what you're doing. Yeah, I see what you're doing.
There you go. Hopefully that works.
I left my
I
soda
don't have
in
a
the
backup.
freezer.
Sorry?
I left my soda in the freezer, so it's completely frozen now because I forgot that we were doing the show, and it's like all over me.
Maybe we should switch to you. Okay, there you go. So we have our data set, random and not random now. what I'm going to do is, you know, basically have a split function. So basically, I've copied.
Can we, because I think it's going to be useful, I think we should clear out some of the data in the random, not random one, just because I have a lot of images that are just black because there's not enough light.
Let's try. Let's build a model.
Okay.
Let's try to get, and then we can improve and see what's wrong. So, all right, lighting. I'm going to be coding in the dark. I don't know. Let me just get up. There you go. Okay. I think it's called Randall. I'm just going to keep the same directory names. Doesn't matter.
All right.
So valid one is not Randall. 0. Randall. Okay.
You know, this would only work with a millennial because I'm the only kind of person who takes 3,000 selfies of myself.
Yeah, I know. Okay. Oh, yeah. Must be valid. Okay, that worked.
That was easy.
Yeah. Now I'm going to create the list file. Randall, not Randall, R and R. I'm just going to call that. So we're creating our list for our validation. These are just list files so we can efficiently generate the record IO files. And we're gonna. Oh. So you can see these are just image operation. We can see we are resizing, we're changing the quality of the images, and it's pretty efficiently implemented in C++. As a Python equivalent as well. So the input images need to be in the same shape.
Yeah. So this is just casting them all to that shape and grayscale
Correct.
and all that other stuff.
Yeah. So this becomes our. I added an extra prefix. It doesn't matter. But train. There you go. That's our data set. Okay. So that worked. So you can see here we're shuffling. We're saying, hey, you can crop, you can mirror. So we're augmenting the data set and enhancing that as well.
I didn't
So we're
realize
creating
it had those options too. It must have a bunch of different things.
It's pretty cool. Right? So we basically enhance our data set even because we only have like say 3,000 images of you.
You can crop it and rotate it and all these other things to give it even more different inputs.
Correct.
OpenCV has tools for that too. This is my only other experience.
I mean this is done. Yeah, this is done within the operator itself. So we're done with these steps now. So we have downloaded the model. We will get our training model, and the next thing is actually running the model. So
now we train it.
Correct. So we're going to run it for 2 classes. binary classification.
Randall versus not Randall.
Yeah. Okay. I'm going to use all the 8 GPUs. I don't know. I'm just going to use single GPU with 4 bat size. We'll see what happens. I just want to see some improvements. We'll call the fit function. I'm going to comment this out.
Yeah, we haven't really talked about some of that yet.
Okay, cannot find any rec file. That's because they are in the data folder. Wow.
The lights keep going out?
Yeah.
You're not active enough.
Am I in the same directory? I don't know what's happening here. Get iterators.
It is in the right directory, right?
It is.
Twitch, CNN.
Cannot find URI patterns that match data.
Do you maybe need a / in front of data?
Yeah, could be. No? I'm going to do...
We can always do like os.path.expand user and then just pass in the full path.
Yeah. I'm just going to cheat. Oh.
Still not working?
Yeah.
Maybe it depends on the input split ACC. Yeah, it might depend on the
maybe. Yeah, I doubt it.
If so, we can open a bug against MXNet.
Wow.
So, I mean, what is the file size? That's the other thing that it's checking.
Oh, that's a good point, actually. Yeah, that's a good point. We probably did not do, something went wrong in our step.
Yeah, that's why it's not working. It's because it's...
Look at that. The list file, yep. There you go. It doesn't throw friendly errors.
Yeah. I mean, it does say that in the error message. It's just we had to sit there and read the beginning part of the error message because it looked like the English part of the error message is like, could not find a file type that made sense. But the part before that is, did not match this pattern of file size not equal to 0.
Right. So...
That did complete very quickly.
Yeah, I should have suspected that, I think. So this is... Okay, there you go. There you go.
There we go.
That's good. That is what we want. On our palette. Oh shit. We need this. Yeah, that should do it. Okay. Aha.
There we go. Oh, so this is doing all those rotations and things and creating a lot more images than we started with.
No, it's actually just converting into it's resizing and converting it.
GosuCat says, "Hey, I just tuned in. What are you guys doing? We are building an image recognition model, a convolutional neural network, for determining whether or not something is a picture of my face." Because that seemed like a good idea at the time.
There you go. We've got 218 megs and the validation set is about 6.3.
Gotcha.
Right. Aha.
Okay.
All right. Good catch. So as you see, like I'm still using stochastic gradient descent. I'm not using the optimizer. I'm just using whatever was there and seeing what happens, right? So, but this is what you as a programmer will need to play with. You might use a different optimizer.
Might need
You'll use a
Adam.
different learning rate, different batch size. Like that's what all you need to do. So look at that. That's not bad at all, Randall.
Did it just go to
Like look at that thing.
97%? Wow. Okay.
Yeah, I mean it's really easy to identify you.
I'm a very standout kind of person. I really hope that it's not taking all of the images that are just like 60 KB black images and assuming that if I post a black image, that it's a Randall.
Yeah, I don't know. So let's doesn't that. Okay, we'll save. I wonder how many batches. I will let it go while I build up the rest of the code.
Okay.
So yeah, I'll show you guys how to like load the model. So we'll take an image and see if that's Randall or not. You wanna send me a selfie? Yes. Put a new image in that bucket and let's see what happens.
Do you want to just grab the one from the evangelist page? Does that work? Or does it need to be the same input type?
I can shape because I have the code here to shape the model, so we can use that. So prefix.
If you grab the one from this page, I'll put it in Twitch chat, but I'll also send it to you.
Yeah.
If you just grab the awful photoshopped picture in there, it might be good. Otherwise, I'll send you.
Load model. And then okay, this is gonna be fun. I wish I could just stop the model.
But it has to finish that first epoch.
I kinda can. I'm just waiting to see if it does finish. So let's get everything else ready. So Randall Hunt.
This is a really bad photo of me, by the way. This is my badge photo. But you can get that if you need to.
No, I have the code to do. Oh, nope, not that. Delegate. Oh, I think I just stopped. Anyways, yeah, I shouldn't have done that, Randall.
You shouldn't? Do we have to start again?
Yeah. No, I accidentally.
Do we need to do module.save instead of, or?
No, that's fine. Like the module variable wasn't available for me because I stopped it. It was not in the context.
Oh, right. Where did we define the number of epochs? I didn't see that.
Here? Oh, good question. By default, it just takes one. I think we declared it. Yeah, I'm just using the default epoch.
Okay, it's going faster this time. It was only doing 12 samples a second last time.
Yeah, because I'm using 4 GPUs.
Have you shut down all of the other models that you're training?
Think so. So the other one, oh well, the other model we tried earlier, we still kind of got stuck at 88%.
Right.
Seems like we need we need changes in the filter size, perhaps. We need to make the model a little more complex, I feel, to get better results.
Maybe some rotation and stuff like that.
Yeah, more data and so on.
So adding another layer didn't really help us in that case.
Correct. So the adding layer, yeah, correct. It didn't really affect, so which means that maybe we lack the data, maybe the filter size. So you kind of like can start debugging from that point.
So is adding another layer in the convolutional sense? Is adding another layer the first thing that you try, or?
Yeah, you can do that. Yeah. So it depends on more layers, but more layers need more data. I thought I had more data, but
Right.
clearly I didn't. So yeah, you play with this, then depending upon the results you see, well, so you kind of build on that intuition. So it's a lot of like debugging, like code-like debugging, kind of see what the network is telling you, what the process is telling you, and then kind of.
So we have some people in the Twitch chat asking if we're working on Skynet. No. This reminds me. So Boo Boo Fox asked if we were working on Skynet. I'll go ahead and say no. But I, for one, welcome our new artificially intelligent overlords. And then Gosu Cat says, this reminds me of something the NSA would make, and I'm sure the NSA has already made this. And then Threadberry says, how are you feeling today? I'm feeling pretty good. I can walk.
I think
we might.
I'm going to use 80 GPUs. Well, yeah. I've tried too many things now.
We gotta run again.
Yeah.
That's some of the issue with some of the C++ bindings is they don't cleanly detach depending on how the kernel is stopped or how the execution is stopped.
Yeah, that's true. I think I'm using this. Okay. Clearly, there you go. Look at that, right? not happy. We've got a bunch of things running on all the GPUs.
Yeah.
So,
Can we clear all those? Like if we just psaux or pgrep for Python, or I don't know.
I don't want to kill all the stuff. Maybe running something important.
Okay, so Threadberry asks if we could get a Amazon Lumberyard game lift session. I could probably do a Lumberyard session, maybe around the November timeframe. Game lift, I don't have enough people who would want to play a game that I would need a game lift, really. I mean, I can demonstrate game lift and I can demonstrate the matchmaking components, but you guys would all have to download an executable, and then we would have to artificially limit my number of servers to 0 so that it would spin up an additional server. And then Hello World for connecting Lumberyard, AWS, and Twitch. Maybe I can get somebody from the Lumberyard team to come and do that. They have their own Twitch channel that you guys can check out, the Amazon Game Studios Twitch channel. So if you look at Play Breakaway and those games, they have a good Twitch channel as well. Hope that answers your
Well, I'm
question.
trying to speed up this entire process, and things are not being friendly.
It's going slow.
I think, unfortunately, I was trying to get it in the next 2 minutes, and we'll probably need to stop here, Randall.
That's fine. Randall
We
or
will
not
come
Randall
back.
doesn't need to exist anyway.
No, we'll show. No, the code is there. We know it's training. It's probably going to get things right, but we just don't know how. It might just take us, 10 minutes to get this running, and our stream needs to be closed. So I don't know if you have ideas. Maybe we can post this a little later. So I'm going to run this in the
Sure.
background, and we'll post it in the Twitch stream or Twitch chat, or we'll just have this. We'll just tweet out, and you guys can take it from there.
Okay. I am going to say that I think you're probably going to need to remove some of those all black images to make the model train, if not faster, better.
Yeah.
But the good news about those all black images is that they're all like less than 100K. So you could just do like find.name JPEG size 100K dash delete, and it'll go through and delete all those.
So for folks like who want to just go play with the code, the fine-tuning code that I showed is already up on GitHub. So I'm posting the code, so you guys can go start. This is an instruction. It's very detailed. You can download this data set and get it going to basically identify cats and not cats, or cats and dogs in this case.
All right.
Cool.
Well, thanks again for putting up with me and teaching me through a 2-hour-long series of questions. Anything else that you want to close with? Anything that you want people to know about the next session?
Yeah. So people, folks, you can go to this GitHub link. All the code is uploaded here. As you can see, episode 1 and 2, the code's already up. I'll post the code that we did today, probably end of today or early in the morning. So go check this out, run the labs. The sessions are recorded. Feel free to send questions, send us feedback. Also, if you have some cool ideas or data sets that you want us to model and work on, I'm happy to take that on. So next week, I'm still deciding on what to do, but we'll probably do neural machine translation. We'll kind of explore how we can, convert from French to English, French to German, and kind of play with language conversion there.
I speak those languages, so that's fine.
Awesome.
I can grade our translation.
Cool.
And I'm really excited to say this Twitch user's name. What? That's his name. It says, will this be available on YouTube or somewhere else later? It will be on the Twitch channel maybe 10 minutes after this recording, and it'll go to the YouTube channel in a few days, I guess. But you can get all of the information about the Twitch series, not just about the stuff that we do, at aws.amazon.com/Twitch. And I'll post that link here. And you can see all the different episodes and stuff that we run. So, Sunil, thank you so much. I had a good time today. I learned a lot. I feel like a bunch of different concepts finally clicked together in my head.
That's great.
I am going to go and play with some of this, and that's it. Bye.
I'm gonna hold you. I'm gonna hold you up for that.
Okay.
Cheers, guys.